What is calculus? Calculus is a branch of math invented about 400 years ago to solve problems in physics related to things that change, rates of change. We're going to motivate this with two examples. So we're going to start with something called the velocity problem, and then in the next video we'll talk about something called the tangent problem. So let's say that you love this first calculus course and you love it so much that you're going to go on and do an engineering degree, and you get hired by some company that makes these wonderful levitating magnetic trains, and they hire you to design the train. And there's the big unveiling day, and here all the politicians with their red ribbons and giant scissors and all this kind of business, and there they are talking to the reporters, and they say, our train is so wonderful and we are so proud of our engineers. They have been able to figure out that the position of this train at any time starting from its nose will be related to this simple formula. And it's a function of time. And so all the audience members applaud and everything's great. And one of the reporters then asks, could you tell us how fast is the train going at time t equals 10 seconds? There's a good question. And of course, all the politicians don't know. And then they turn around to your boss, and then your boss turns around to you and the pressure's on. How do you figure out how fast this train is going? Could you explain it to them? So this is the kind of question that we're interested in. Now, you've probably taken a physics course at some point in your life. So you may or may not remember that velocity is related to change in position over the change in time. So we'll say that velocity, delta S, so this triangle is a symbol for change in, over delta t. So change in position over change in time. If you're interested in the velocity at time 10, maybe we'll say it'll be the position of this train at time 10 minus its initial position over the final time, which is 10, over the initial time. Delta means final minus initial. You've got your formula for the position of this object at any time. And because it's function notation, you know that wherever you see this letter t, whatever value you put in goes and matches that spot right there. 10 squared is 100 times 4. You're going to get 400 minus 0 over 10 minus 0. We'll get a 40. Now, we're going to assume that the units of position are in meters and that the units of time are in seconds. This should have units of 40 meters per second. So should you tell your boss that the speed of the train is 40 meters per second? The answer is no, you shouldn't. This is what we call the average velocity over the first 10 seconds. This number says, well, you traveled 400 meters and you took 10 seconds to do it, so you could be going uniformly at 40 meters per second the whole way. But in reality, that's not what happened. Your train did not start instantly at 40 meters per second and preserve that. It probably starts from 0 and it kind of takes some time to ramp up and get faster. So this is not what we want. We don't care about what's happening at time 0. So what we want is something called the instantaneous velocity at time 10. The root word of instantaneous is instant, and that means we want the velocity right at that exact moment in time. So at exactly that instant in time. Okay, no problem. We can figure that out because I know how to calculate velocity. It's change in position over change in time. So how about we do something like this? The velocity, and I'm going to use this notation, velocity at time 10, so we'll call this the instantaneous velocity, is going to be s of 10 minus s of 10 over 10 minus 10. If you don't care about what's happening at time 0, don't include it. If all you care about is what's happening at time 10, just use that one. Well, you might think that's sensible, but you're going to run into a problem. When you plug it into this wonderful formula, it's going to give you 0 over 0. Now, this is essentially garbage. As soon as you have a 0 in the denominator, this is undefined. There's no way to divide anything by 0. It doesn't make sense mathematically. 0 over 0 is math's way of telling you screwed up something. This entire calculation is garbage. It's not going to give you anything useful. You need to tackle it in a different way. So starting at 0 is no good because we don't care about what's happening at 0. We only care about what's happening at 10. Narrowing into time 10 is no good because we don't get anything useful. And so way back in the day, the pioneers of all this stuff said, this is a tricky problem. How are we going to solve this? And the light bulb went on. They said, oh, yeah, I don't care about what's happening at 0, and I'm more interested at what's happening at time 10. So rather than going right to time 10, why don't I just go a little bit closer to time 10? So I'm going to consider the average velocity on some time interval near 10. Not exactly at 10, but near time 10. So now I'm going to be using what's called interval notation to write this down. So let's say, for example, I'm going to take a time interval that goes from 9.5 seconds to 10 seconds. Delta t is going to be final time minus initial time. It's going to be 0.5 seconds. And if I were to calculate the average velocity on this interval, I'd take my position function, 4 times 10 squared, subtract 4 times 9.5 squared, 10 minus 9.5 on the bottom. This is the number I'd get, 78 meters per second. It's totally different than the number we got before, but it should be. Is this the instantaneous velocity at 10? No. I don't care about what's happening at 9.5 seconds or 9.6 or any of those. I just care about what's happening at 10. If you don't care about 9.5, then go closer. How about we start at 9.9 seconds? Throw away all that other junk. You don't need it. This time, the size of the time interval, it decreases down to 1/10 of a second. So if we are to take the average velocity on this time interval, final position minus initial position, divided by final time minus initial time, we end up with a different number, 79.6 meters per second. Ending up with a different number is not bad. As I make that time interval smaller, the answer that I got didn't change as much from the previous one as it did from when I started at time 0. I don't need 9.9. I don't care about 9.9. I just want to get closer to 10. So why don't we take another time interval where we get even closer to 10? This time we're talking about 1/100th of a second. Do the same stuff. Final time minus initial time. And if you were to sit there and take this calculation, what you would get is 79.96 meters per second. So again, the answer you get is different, but it isn't that much different than the one you got before. I can keep making that delta t smaller and smaller and smaller. So we're going to come up with this new notation. I'm going to put this arrow here as delta t with an arrow going to 0. This is math symbol for approaches. So as the size of the time interval approaches 0, probably seems reasonable to think the average velocity approaches 80 meters per second. You don't really know if that's going to be the case, right? It might end up being 80.000007 or 79.9999993 or something like that, but you're taking a guess. So my guess for the instantaneous velocity at time 10 would be 80 meters per second. And if I were to take a different time interval, so maybe let's say I'd take values that were larger than 10 and shrink them down to 10, I would find a very similar thing in this case, that the velocities would get closer and closer and closer to 80. And so this idea where you have to change the size of the time interval was the breakthrough. This was what the pioneers invented hundreds of years ago. And they said, aha, this is a good way to come up with instantaneous velocity. This is something that we're going to call a limit process, and it's being applied to average velocities on time intervals. And these time intervals are going to 0 in size. They don't actually get to 0, because if we make the time interval exactly 0, then we're back to that business before where we were dividing 0 by 0, and that gives us nonsense. So instead, what we're doing is getting as close to 0 as we want without actually getting to 0. Now, in terms of notation, the instantaneous velocity at time 10 in this problem, we're going to write this LIM for limit delta t going to 0 of the average velocity. So the instantaneous velocity at time 10 is the limit process applied to the average velocity as the size of the interval goes to 0. We are taking the position function at some time 10 plus delta t, take away the position at some time 10 plus delta t, subtract time 10. These 10s will cancel out. And what we end up with is some limit as delta t goes to 0, s of 10 plus delta t, subtract s of 10 over delta t. This is the set of steps that I'm following to get the velocity at time 10. Now, if I wanted it at time 20, I would just swap out all the 10s for 20s, but the process would be the same. So in the next video, I'm going to show you how the limit process can also help us solve problems to do with tangent lines.